involved and think it's fun and want to do it, but they just aren't capable of doing it.
Because that's what I don't understand about the last night's group, because it wasn't like they were that old.
Like,
right, but
the lady running the show, they don't want to say anything. She kept calling.
Yeah, and she kept making call after call after call that was not right.
They were double teaming Jordan.
Yeah.
She never got any calls.
mm-hmm. Yeah, it was.
Smacked him.
Yeah, it was bad, but not the worst I've seen, unfortunately. Oh, I want to give you a homework problem. So, I don't want to give you homework. I'm pretty sure I do. No, sorry.
I guess you're right.
Well, I mean, it is optional. You don't have to do it if you don't want to.
Oh yeah, let me just take a
That's
good 90.
Actually, the lowest day in here is an 85. So.
Yeah. But you don't do any of the homework. It's zero homework. But you get that's just
See, the issue is, I don't do
oh.
Not Monday. Not Monday. You do know that we're not having class a week from Friday, right?
What?
No.
That's my fault.
Oh,
We were talking about that.
We're not going to be here anyway.
Chelsea didn't want to be here either, so.
We're not.
We're going to talk to him.
We are not going to have class on what day that is. The 6th.
Is it the series?
Is that a special
I'll be in Vegas.
Yeah, it's.
Spring break.
It's Sergeant Joe.
No, he will.
Starts Friday
Dr. Roth will have class, but we will not have class. We won't have Lillian either.
Oh, yeah.
I was gonna say, Dr. Rollins is going to have class.
You should tell Dr. Roth not to.
Not to what?
Tell him it's snowstorm.
You'll have to take it up with Dr.
I was
Roth.
gonna say, we also have the option just not to go to class.
It's true. You could not go to class.
I could go home.
Yeah, I don't think he actually has. Is he given it to the Rollins?
No.
Roth? No.
No.
We're good. I think like 20% of the grades like participation.
Okay, well, I participate, so I'm good.
On the syllabus. On Dr. Ross syllabus.
I've never seen this.
What? What's wrong?
I can't read.
Oh,
Dr. Jones.
yes. What's that?
Yeah.
Oh, yeah, she did. I forgot. I have that. Thank you. I forgot. Thank you for reminding me.
No problem. Anytime.
That's old one, actually.
Dr. Joe, is that Excel spreadsheet all you wanted? I didn't know. I said, that's me for an Excel spreadsheet.
Because Haley asked me for the Excel spreadsheet, so I just forwarded it.
Oh. I did one problem. So.
She asked for it, and then asked if you had it.
She was telling me that I didn't put my homework in, so I was like, that's just untrue.
Actually, that's not what she said. She said there was not a homework in the stack with your name on it.
Which she pretty much implied of I didn't do my homework.
It may have been implied, but all she said was there was a homework in the stack. There was no homework in the stack that had your name on it.
Oh, it didn't.
Yeah. So that was what she wrote. That was what she was saying. She didn't lie. She just said something different.
I love how she put my soccer number.
Yeah. Yeah. You have a complaint, Sam?
Yeah.
The complaint department is next door. What's up, Sam?
I calculated Z-score, and Haley calculated the wrong Z-score. It said Z of 0.025, 1.645, and it's 1.96. You'll have to show it to them.
I mean, later. Later. You can show it to me later. All right. questions about anything before we get back into what we were talking about last time?
What were we talking about last time? We were talking about the stuff before.
Yes. We were. That's not.
It's off the type one error.
Oh, yeah.
I feel like you read.
There it is. Trying to find the right page where I was.
One shows and
All right.
take off the
She took a point off of me because I didn't write it the way that she thought it was so good. She called it an inconvenience fee.
That's great.
That's fun. All right. So we started talking about the ideas of hypothesis testing last time, which is pretty much all we're going to do for chapter 7 and 8, for that matter. And then, actually, when we talked about 10 and 11, it's also about hypothesis testing, just a little bit more theoretical. So a lot of what we're going to be doing the rest of the semester is about hypothesis testing. So, all right. Anyway, so we started talking about how we would hypothesis test for proportions. So, this is just the first problem in the homework that's on page 349. The exercise is on page 349. So we started off talking about these different bowls that had a different number of red and white balls in them. And like I mentioned last time, for ever and ever and ever, you've drawn balls from bowl A, and then some prankster comes along and says, hey, I may have switched bowls on you. And you want to try to figure, it was Michael who came along and did it, yes. Came along and said, I may have switched bowls on you, and you're trying to figure out whether or not the person switched the bowl. All right, so the way we're going to do it is, in this particular setup, was we're going to do 3 balls and see if whether or not you can determine from the sample of 3 balls if the bowls have been switched. To determine whether or not they've been switched, you need to figure out a way to make this determination saying, oh, I reject the null hypothesis, something has changed. That's the rejecting of the null hypothesis is the words that we use. Something has changed if I take out a sample of 3 and there's 2 in that sample, or there's 3 in that sample. Okay. So we always make the assumption that the null hypothesis starts out being true, and we're trying to see whether or not there's enough evidence to conclude that it's not true anymore. Again, usually the idea behind this is you've had something that you've had in place for years and years and years, so that you've got an idea of what the parameter is supposed to be. And then you make some sort of a change and see if the parameter has changed based on, at least in part, whatever change that you made. Right. So you've manufactured a light bulb the same way for 50 years. You have a good handle on how long that light bulb lasts. Come along and there's a new filament that you can put in the light bulb that's supposed to make the light bulb better. You want to create a light bulb, the new light bulb using the new filament, and test how long it lasts and see if you've actually made an improvement before you switch all of your processes over to make new light bulb. Right? Those kind of changes are costly. You wouldn't just want to just change it over and say, hey, we got a new light bulb, without actually seeing if that process made the light bulb better. So you need a way to test it and say, from this small sample of making these light bulbs, did it make a better light bulb? Before you switch everything over, right? So the whole idea of all of this is either you've had something the same way over and over and over and over again, and you're making a change to see if the change made a difference, or you've got 2 populations and you're trying to compare the 2 populations and seeing if there's a difference between them. Those are kind of the ideas behind a couple of the main ideas behind hypothesis testing. So this here says that when we're finding this rejection region or critical region, those both mean the same thing. If I say rejection region or critical region. In this case, we said that we're going to set it to, if there's 2 red balls in the sample out of the 3, we will say that it's rejected. Or if all 3 are red, we'll say that it's rejected. So what's the probability that you actually land in the rejection region, but the null hypothesis is still true. And that was the last thing I think that we did on Monday. And when we calculated that, that gives us our probability that you actually reject the null hypothesis and it's true is, in this case, a little bigger than a quarter, 7 out of 27. So this is a bad thing to happen, right? When you reject the null hypothesis, but the null hypothesis is actually true, this would be a bad thing to happen. So we would want this probability in general to be small, much like the alphas were small when we did confidence intervals. There's a lot of overlap between confidence intervals and hypothesis testing. Okay? We want this to be small, and so that small probability, the alpha, that we reject the null hypothesis when it's actually true, that's the significance level of the test. All right, so this is actually the probability that we make this type of error. That's what the alpha represents. So that's what's referred to as a type 1 error, is when you reject the null when the null is actually true. You don't want that to happen. Okay? Well, you never want to make errors, right? You want to be as robust as possible, correct? You want to reject when you should and not reject when you shouldn't. All right, those are the good things. All right, so this would be a bad scenario if you actually rejected the fact that, yeah, the bulls were switched in this case, or sorry, rejected the fact that you still had bull A based on this, but you really did still having it out of bull A. I don't know what consequences there would be if you were switched, pulling these balls out of a different bowl now, or the same bowl, but that's the idea, that's the bad thing that would happen. What's the other bad thing that could happen? Not rejecting when you should reject, right? Okay. So in this case, I'm still on red from the last class. So what if H1 is true, but you don't reject? So we can calculate this probability as well. So this would be the probability that X is not in our critical region, but this is a conditional. This would be given that H1 is actually true. Yes, HA, yeah. H1 and HA are the same thing. And I probably will use them interchangeably. I'll use H1 when I'm thinking about what they have in the book, and then when I'm not thinking, I'll use HA because that's how I learned it.
That's how I learned HA.
Yeah.
This semester.
Yeah, no, I know. I know. I'm trying to be consistent with the notation in the book, but my brain doesn't work correctly, so I will switch over to the other one. Yeah, it's not in the critical region when it should be. Because the critical region is what we use to reject. So what's the probability that we don't reject when we're supposed to? We're supposed to reject when H1 is true. So that's why we have it written that way. So what's the probability that you're not in the rejection region, not in the critical region, given that the the alternative hypothesis, the H1, is true? All right. So if H1 is true, what's our probability? What's P in this setup? Remember the null hypothesis was P was 1/3. The alternative hypothesis was P was 2/3. So what P are we going to use for this setup? 2/3, right? Not being in the critical region means you had no successes or one success in this case, right? So we would have 3 choose 0, 2/3 to the 0, 1/3 cubed, or 3 choose 1, 2/3 to the first, 1/3 squared. So what do we have? 1/27th and then another, I think it's the same value, isn't it, that we had before? Yeah, it sure is. So this will be 2/9. This doesn't always happen, by the way. Was it 7 out of 27? So this one actually ends up being the same thing. It's because of the symmetry that they set up the problem. Yeah, Morgan?
So when you say when H1 is true, but you don't reject, is that like you don't reject null?
Right.
So you're inclusive?
Yeah. What's wrong?
My whole window.
And now you're cold? Well, then shut the window.
Don't shut the window. It feels good.
Let's go over there and shut the window. Don't let him bully you. I know.
That is bullshit.
All right. So anyway, this, by the way, these two numbers turning out to be equal is a coincidence. It doesn't typically happen this way. Okay. The reason why it happened in this case is because of the symmetry of the problem. All right. So this is the probability that you don't reject when you should. So this is the probability that we do not reject H0 when H1 is true. We refer to this probability as beta. Beta has something to do with, I'll say, the robustness idea of the test, and we'll talk more about this later when we get into trying to find what are referred to as most powerful critical regions. Okay, you want to make your test as robust as possible. Or like I mentioned last time, you get to set the significance level, right? But the beta depends on lots of different things. So you have to try to figure out a way to get some handle on beta, but you don't really get to control it. You don't get to pick it, I should say. You get to control it in some sense, but you don't get to pick it. Yes, Sam?
That probability that you're buying is that
This is, I mean, just for the context of the problem, it's you want them both to be low because you don't want to make errors. So in both cases, these would be relatively high. You want them to be as small as you can make them. Now, it's possible that you can make your alpha low, but your beta is still high, depending on how the test works. Yeah, great. This is a type 2 error. Yep. So this is what's referred to as a type 2 error. And beta is your probability of that happening. Okay. So, again, your alpha is your probability of type 1 error. That's your significance level. Your beta is the probability of type 2 error. You don't reject it when you should. So, 1 minus this, if you did 1 minus beta, that is the actual probability that you reject and you should, right? Your X is in the rejection region and H1 is true. Right? If I do the complement, that would be X is in C given H1 is true. The complement of that conditional probability. That's what's referred to as the power of the test. You want high power tests, so you want betas to be low. However, it's hard in general to calculate beta. Beta depends on what the true parameter is. In this particular problem, we have what are referred to as simple hypotheses for both your null hypothesis and your and alternative hypothesis. Right? We had P was equal to 1/3. That's a simple hypothesis. We had the alternative was P equals 2/3. That's a simple hypothesis, right? Okay. Usually, and in almost every single problem that you will do, your alternative hypothesis will be a compound hypothesis. It includes lots of different values. So usually, your alternative hypothesis will be something like P equals 1/3. Sorry, your null hypothesis will be P equals 1/3. Your alternative hypothesis will be P is greater than 1/3. Or P is less than 1/3. Or P is not equal to 1/3. Okay, different from 1/3. That would make this computation much harder. Because if H1 is true, there's lots of different values for the parameter that will make H1 true. So I won't be able to calculate the power, or this beta, exactly. Because I don't know what the actual value is for the beta. Or excuse me, for the parameter. I keep saying the wrong word. I have to know what the actual value is for the parameter to be able to calculate these probabilities exactly. So if I have a compound statement for one of the parameters, then I can't calculate the probability exactly. Now again, I told you that for the alpha, we have to be able to pick the probability that we make a type 1 error. So our null hypothesis will always be a simple statement. We think we know what the parameter is now. We want to see if the parameter changed to something else. Is it bigger? Is it smaller? Is it different from? Okay? That's the idea. Yeah, Sam.
So if people want small out there, the model rate should take like 99.999%.
Because to get that small of an error, you have to take huge samples typically. And taking huge samples is costly. From time perspective, from materials perspective, lots of different perspectives, it's costly. So you want to be able to make a conclusion based on information that you can actually obtain. Because we've seen things like, to get within a 3% margin of error, you need, 2,000 people to go survey, right? But if you wanted your margin of error to be 0.000001 or something like that, you're going to need significantly more people to survey, and you might as well just have taken a census for the entire population and not done a test, just actually find out what's going on. Morgan, do you have a question?
Yeah. Could you explain how that minus?
That's a definition.
Okay.
The definition of the power is the complement of the probability of making a type 1 error, or type 2 error,
Because when x is in
we want to, the 1 minus beta is the probability that you are in the critical region when you're supposed to be. That's what the 1 minus beta is. And that's how they define the power, that you're actually rejecting when you're supposed to be. That's the idea behind the power. Now again, that's a hard thing to get a handle on because you don't know what the new parameter typically is. You know what the old parameter is based on past experience, but you don't know what the new parameter is, right? If I have an old light bulb that lasted 1,000 hours and I make a change to that light bulb to see if the lifetime improved, I don't know what the new one is because I haven't made it yet. I think I have a new process. I think it's going to make an improvement, but I don't know exactly what it is. If it's better, is it significantly better? Is it only a little bit better? I don't know. So it depends on what the actual value of the parameter is. So the power varies depending on what the value of the parameter is, which is why I said it's harder to get a handle on. Ordinarily, you can't calculate the beta without knowing the exact value of the parameter that you're trying to figure out. Which is hard since you don't know the value of the parameter that you're trying to figure out. So basically you're just seeing if there's a change or not. Now, there are some other things that we can do to say, okay, well, how likely is it that a sample was at least this good? So that tells you a little bit about your, confidence, if you will, and how likely it is that you're wrong. So we'll talk about that in a minute when we actually do a test. So let's do another one. Let's look at 7.1-3, just to try to get a little bit more handle on these definitions, and then we'll do some actual honest-to-goodness types of things that look a little bit more like standard hypothesis testing. So 7.1-3 has a binomial random variable y, and the null hypothesis is that the p is 0.08, and the alternative hypothesis is that the p is less than 0.08. We're going to reject if we look at y and see if, oops, the number of successes that we do is actually 6. So y is, we're given the n value here for the y. So there's 100 trials, but we don't know what the p is. Our null hypothesis, our status quo is that the parameter value is actually 0.08. We're going to test to see if the parameter really is less than 0.08. Do we have enough evidence to conclude that the parameter is actually less than 0.08? So we're defining a rejection region that says that their y is less than or equal to 6. What's wrong? Sorry. Oh, less than or equal to 6? Sorry. Yeah, it's a 6. All right. All right, so our rejection region, again, is defining when we're going to reject. So the first part of this asks, what is alpha? What's the significance level? That's the first question it's asking in this problem. So alpha, again, is the probability that you're wrong, that you make a bad rejection, that you reject when it's true. So you want to know what's the probability that, in this case, y is less than or equal to 6, because that's the rejection region, given that p is equal to 0.08. Or use Excel. So let's see here. Let's go over to Excel. Assuming Excel will open sometime today. All right, so that's what Excel does. There's also a binomial CDF on your calculator.
Oh, yeah.
Yeah. All right. So in Excel, there's a binomial distribution function. Binom.dist. All right, so the first number that you put in here is number of successes, so that's 6 in this case because we want y is less than or equal to 6. The number of trials is 100. So we just type in 100. The third thing is wanting to know the probability of success. Now remember, we're calculating alpha. Alpha is the probability that we're wrong, that we rejected when we're not supposed to. The probability that the null hypothesis is true, and you land in the and that you land in the critical region. Okay. So the null hypothesis is true is what the assumption is for this. So what's the probability of success then if we're going to assume the null hypothesis is true? 0.08. Good. So 0.08. And then I need to tell it's cumulative because it's less than or equal to 6, right? So I'll say true for cumulative, just like the other ones. So there's the syntax for this. And you get 0.3, which is really, really high for a significance level. Okay? But that's what they asked us to do in the problem. So, what's that? No, I'm not going to, just because you asked. That was needed. Yeah. So the true is for cumulative. All right. So the significance level then is about 0.3. You okay with? Can I hit it now? Okay. There's a 30% chance that you're rejected when you're not supposed to.
That's a no-brainer.
Yeah, that's not good. All right. So part B asks you then to go the other way. What's the probability that you made a type 2 error? What's the probability that you didn't reject when you should? Now again, remember that the alternative hypothesis here is a compound hypothesis, is that P was less than 0.08. So the problem asks you, I'll write it down and then I'll flip back over to Excel, but just so you can see what it says. The problem asks you to find beta if, oops, P is actually 0.04. So again, beta is your probability of making a type 2 error, the probability that you didn't reject when you should. But in this case, to be able to calculate the beta exactly, I have to know an exact value for the parameter. So in this case, it says, what is beta if P would happen to actually be 0.04? They're just picking one out, yeah. Usually what you can do with these is make what's referred to as a power curve. So you, for various values of the parameter, you would graph the power function. So it's actually a function that you would graph. We're going to talk a lot more about power later. So I'm kind of just waving my hands at it a little bit. But so as the value of the parameter changes, you can check what the power of the test is. That's what the power function is. All right, so going back over to Excel then, it's going to be the same command. Whoops, except I want to be not in the critical region, right? I want to not reject when I'm supposed to be. So I want to be not in the critical region given the alternative is true. So I have to do 1 minus that, right? Because I want y is greater than 6. Okay. So I want 1 minus binomial distribution. 6 was our critical region, right? Still 100 trials, but what's the probability of success going to be in this case if we assume the alternative hypothesis is true? 0.04, and then true again. So again, the reason why we want to make sure that we use, the reason why we want to use 1 minus here is because we want to be not in the critical region when we want to. The critical region would just be this part, right? The probability of being in your critical region is just the end piece here, right? So 1 minus that is the probability you're not in there. Okay. So if I enter that, then we get about 0.1. It's better. I'm not sure good's the right answer. All right. So what would happen if we changed this to a different number, say? Instead of 0.04, what if we changed it to 0.03? Do you think that beta would go down or up?
Go down.
It should go down, right? Which it did. Why? Well, so in that case, the two parameters are farther away. The probability that you're wrong is a less likely. The probability that you didn't reject when you should is much smaller because the probability of success is much smaller. So you're going to get fewer successes in your sample, most likely. So it's harder to get 6 or more successes the lower the success goes. Or sorry, 7 or more successes the lower the probability of success goes.
So the probability goes down.
The power should go down. Or the probability of making a type 2 error should go down. But if it were 0.07, then it's really bad.
But if the type 1 error, if the probability goes down, then does it go up?
For the type 1 error?
Yeah.
Well, we get to pick this, so that if we were doing trying to lower the type 1 error, then I would change this number to say 5 instead of 6. That would make it go down. But then that would also affect this. I would have to change this to 5 as well. Yeah. So, and that would make that go up because you got a larger region that it could fall into. Yeah.
So to lower the probability, lower the number. What is our 6?
The 6 is just trying to get it's just a number that they pick to say it's probably not very likely to have 6 successes if the probability is lower than this. So usually you're going to make that be a number that's as much, like 0.05 is a pretty typical one, like 95% confidence. So you would go back up here and maybe try 3, say. That's around 0.05, so maybe you would make it 3. But if I did that for 3 here, then that's really bad. Because the probability that I make a type 2 error is significantly higher, right? That's really, really bad. So that's the idea, is if you try to make your significance level lower, it seems kind of a weird way to say it, but the significance level is the probability to make a type 1 error. That's a lower idea. You want to be more confident, then you're going to change what the other probability by whatever value. The only way that you can really make both of them happen at the same time is make your sample size bigger. Yeah.
Last question.
Yeah.
So if we take 1 minus the type 2 error, that'll give us
The power, yeah. So basically,
we want bigger power.
You want bigger power, yeah. So if I do 1 minus that, I get 0.075-ish. It's not very powerful at all. It's a pretty cruddy test. All right. It does kind of stink. All right, so a lot of this stuff is going to go back to using the normal distribution and the t-distribution and the chi-square distribution, depending on what the hypothesis testings are, rather than doing these things with the binomial. So let's see if we can do an example here. Let's look at, say, 7.1-9. So this is a hypothesis test on the proportion of Americans who like to go run. I do like to run. I ran this morning.
How long?
I did 3 miles this morning on the treadmill.
I don't know, this is nuts.
I didn't go outside. I'd be nuts in the snow.
You don't want to do that?
I fall enough without being on the snow. I don't need help.
Learn more count.
Not when you turn the incline up. All right. So in this case, it says that the proportion that let's see, it says a claim. Well, it's just made by claim that it's just a claim that's being made that the proportion of Americans who select jogging as one of their recreational activities is 0.25. So that would be your null hypothesis. A shoe company thinks this is actually bigger. So your alternative hypothesis would be greater than 0.25. You just want it to be bigger? All right. So they want to test this. They use a random sample of 5,757. That's the total number of people that they sampled. And then the success is 1,497 selected jogging. All right. So we want to test whether or not the null hypothesis is true. So we want it to be, hopefully this is greater than 0.25, but otherwise it'd be a stupid hypothesis test. All right. So let's think about how this works. Well, I don't want to use the binomial distribution necessarily to do this every single time. But we know that once our n gets big enough, we can approximate the binomial distribution with a normal distribution. Right? Once our n is large enough, and our n certainly here is large enough. Okay, 57, 57. So it's certainly large enough to approximate here. So the idea is, if I have an alpha, if I think about the normal distribution, now remember, alpha corresponds to the probability that you reject when you shouldn't, right? So we assume that we're somewhere in the middle here, correct? We're assuming that this is our mean, whatever that happens to be. We're assuming the mean is the mean for the null hypothesis. Okay. Now, for this particular this particular hypothesis test, our P is being purported to be greater than the 0.25, greater than what the mean would be. Now, our mean, of course, for this, if we were doing the normal distribution, we would do n times P, correct?
Yeah.
Right? Okay. That's why we just wrote a mu, because I'm just kind of doing this generally for the normal distribution. But we want to be greater than that. We want to see we want to see whether or not the null hypothesis is true, whether or not we should be concluding that the alternative hypothesis is true instead, right? So this about the mean that we're talking about for the normal distribution corresponds to the null, right? We always assume the null is true to start with, right? Now we want to look at whether or not it's bigger in this case, right? So we're going off to the right. So we want our alpha to have the probability that's in here, correct? This is where we want the probability to be. That's because it's greater than. If it said less than, where would we want the alpha? On the other side, the left tail, correct? Okay. If it said not equal to, then we would have to do like we do in confidence intervals and split your alpha into two pieces and put one on each tail. Right? If it said not equal to, you'd have to split it on each tail. So, but all that means is that if I want this alpha to be here, I just need to figure out what this, for the standard normal, what the z sub alpha is. Right? So then your critical region, the C, would be all values for x that are greater than your z sub alpha, landing in that rejection region. In this case, that's what it would look like. So again, just to recap, we're finding the z sub alpha that leaves an alpha probability on the right-hand side. Okay? And the reason why it's on the right-hand side in this case is because we're doing greater than. If it were less than, we would do on the left-hand side. Either of those cases is what's referred to as a one-tailed test, because all of your probability is in one side. So this is a one-tailed test. If it were not equal to, you'd have to do like we did for confidence intervals, split your probability into two and do a two-tailed test. And then you would be looking for z sub alpha over 2, rather than just z sub alpha. Okay. All right, so this is our critical region. Well, how do we figure out if this sample was likely? Well, remember we want to do standard normal, we would have to, if y is the number of successes, then if we want to standardize that for a standard normal, I would have to do y minus NP, correct? Because that would be the mean, yes? And then divide by the square root of n times p times 1 minus p. Because that's the standard deviation. N times p times 1 minus p is the variance for the binomial. All right? Now, ordinarily, we don't write it this way. Ordinarily, we divide, since we're doing proportions, we divide everything by n to make proportions. So you would write this as y over n minus p over the square root of p times 1 minus p over n. And this looks a lot like what we did for confidence intervals, doesn't it? I hope it looks a lot like confidence intervals. Okay. All right. So for this, our y over n is given to us up here by the sample, right? Here's y, here's n. Correct? So for our purposes, Now, of course, I've already forgot what the numbers were. 1497 over the 5757 is our y over n. What are we using for p? Remember, what do we start with by assuming is true? Yeah, we always assume that the null hypothesis is true, correct? So for p, we're going to use 0.25. And then in the denominator, you'll get 0.25 times 0.75 over 5757. I'm going to calculate that real quick. No, the whole thing. I want the whole fraction.
0.0057.
Really?
Well, I also have it there.
No.
I got 0.011.
Where? Oh, I can do that. You're so funny.
Well, given the way the problem's phrased, I don't believe either of you.
You gotta let me do it.
I've got to keep doing it. I'll throw it ice right to it.
Do you want to get to class on time?
I did it again, I got 1.666.
I'm confident in mine.
That's what I got. All right.
You did 0.25.
Okay, so 1.7577, how does that correspond to what the z sub alpha should be? Well, I didn't tell you what alpha was. Part A said, let your alpha be 0.05, and I know I'm out of time. If alpha is 0.05, z sub alpha is 1.645. So is your z in your rejection region?
Yeah.
Yes. Okay.
Reject.
So we would reject. Okay. We would reject H naught if alpha is 0.05. Would we reject if you did change the alpha to say 0.025? What is z sub, what is that value?
1.96.
That's 1.96. So you would not reject in that case. So again, rejection depends on what you want your level of significance to be. We'll do more of this next time. We'll get into section 7.2 as well, because it's the same stuff just for means. Actually, all of this is the same stuff, except we're just changing context. That's why I've taken extra time to go through the concepts. Because once I get through the concepts, the actual doing of the problems should go quickly. I promise all the problems are the same.
I have a meeting in November, 7 or something like that.
Okay.
That was really fun.